Hi, we are group 0451. We have three group members, Noah, Reggie, and Wei. We divide the work into three parts. Noah doing the eval and pipelines, Reggie doing the build NCMD, UBGFG, and with FG, and me, Wei, doing the signal handlers. Next, let's compile and test our program.
This is Reggie. I'll be compiling the file and running the file. So first, as you can see, it compiles with no warnings. And now I'll be going So the functions I did are built-in CMD and do BGFG. For built-in CMD, I compared the arguments with BG, FG, jobs, and quits. And well, the zero is basically to say that they are the same string. So if it's BG or FG, it calls on the BGFG function with the argument B. If the string is jobs, then it calls the list jobs with the variable jobs. And finally, if the string is quits, the program exits. And then for my next function, it's the do BGFG. So first, we check if there is a PID at all. If there's no PID, then it prints an error message, as you can see over here. If it does have a job PID, then we convert it into the job ID and use it to get the job. And we check if it's a valid job. So if it's instead a PID, then we convert it into a PID and get the job using the PID instead. And again, we check using the same process. We check if the job is null, then there's no such process. And for the final case, if there's no PID or any other case, then we just say that the argument must be a PID or a JID. And then we continue the execution if it was previously stopped by one of the operations. Finally, we check if the string comp is if the argument is a forward or background operation, and we set the state accordingly, and later print out the job state accordingly. This is Reggie again. So for the problems I encountered, so first it was that basically all of the processes just never end. And later on, we discovered that it was because in the part of the stick child handler, we didn't actually have any of the delete jobs. So all it did was just, before this also was a print statement. So all it did was just print statements, and we didn't actually delete any of the jobs. So and then the second problem I encountered was trace spring not working. This was fixed by updating the built-in CMD, which was basically just adding that the string contour should be 0. To be honest, I'm not sure what caused it, but it did fix itself when I add the 0, when I made sure that it's specifically equal to 0. And then for the third problem that we encountered, it was trace 9, where the -spin5 wouldn't kill itself. So we relied on ChatGPT to compare the answers and realize that in the sig child, we need to set the job state to st in order to solve this bug.
For signal handlers, there are three functions in total: sig child, sig ing, and sig temporary stop. First, let's look at sig child handlers. We start by initialize the signal by using sig fail sets, and then we use a while loop to loop through all the trial process and until there are no dead trial to be wraps. And we use the sig pro mask to block all the signal and check if the drop exists, and by using wait if stopped, wait if signaled, and wait exist to remove the drop from the list, to either remove the drop from the list or to terminate the signal. Finally, we restore the previous signal by using sig pro mask. Next, we have sig ints and sig temporary stop. Both of this function, we use the FGPID to get the PID from drops. Then we check if the PID exists or not and kill it by using the argument -PID. And we send the sig int or sig temporary stop signal to the program.
Hi, I am Noah, and I will be doing a code walkthrough of eval and the other functions I wrote to help with pipes. So let's start with eval. These first two lines make a copy of the command line input to preserve the original for later processing. This next bit here checks if the command line includes a pipeline. If so, it delegates processing to process pipeline. It's a function I'll get into later, which handles the complexities of the piped commands. Nothing too interesting here, just some declarations. Here we set bg equal to parse line. This parses the command line into an array of arguments, argv, and determines whether the command should run in the background, bg. If built-in command argv, this checks if the first word in argv is a built-in command like quit, jobs, bg, or fg. If it is, then built-in command executes it immediately, and eval returns without executing the subsequent code. Here we are just setting up our signal blocking. We prepare a signal mask to block certain signals like sig child, sig int, sig stop temporarily. This prevents the shell from being interrupted by these signals during important sessions like around fork or the job addition phases. This forks a new process for executing the command. In the child process, it sets up a new process group and attempts to execute the command using exec vp. If exec vp fails, it prints an error message and exits. If the command is not meant to run in the background, like with this, the parent process adds it to the job list as a foreground job and waits for it to complete using waitfg. Waitfg is right down here, which just is going to wait for the sig child to be received, and we use the suspend with our mask. Then we get into the signal unblocking, where after we set up the job control, signals are unblocked. Signals are unblocked. This ensures that newly created processes or the shell itself can correctly handle signals like sig int or sig stop. The next function I'll go over is set up IO redirection. Here in the for loop, we iterate through all arguments to find redirection symbols, and if we do, we process it accordingly. Let's see, this first if condition here, this searches for the output redirection symbol and confirms there's a file name following it. When found, it sets up output redirection from the standard output to the specified file. Here, we open or create, if non-existent, the file for writing. It ensures any existing data is cleared using these permissions here. And this is clearing the file. Next, we set up redirection with our dupe2 line here. This associates the file descriptor of the opened file with the standard output stream, effectively redirecting all output to the file. This removes the redirection symbol and the file name from the arguments array, preventing them from being passed to the executed command. This identifies the input redirection requests and opens the specified file for reading, setting up redirection so the command reads its input from this file. Similarly, we use dupe2 here as well, which makes the command read its input from the specified file by duplicating the file's descriptor over standard in underscore file no. And here we're just cleaning it up. The next function I'll go over is process pipeline. We are splitting the input command, the command line, into individual commands where a pipe symbol is encountered. Each command is processed or is stored in the commands array, facilitating separate execution of each segment. That's the commands array there. And we set max commands to 10 right there. Then we do some pipe creation for intercommand communication. That happens over in our loop. Oh, sorry, no, right here in this loop. This establishes pipes between consecutive commands in the pipeline. N-1 pipes are created. Here we loop over each command to be executed in the pipeline. This is the child process setup here, where we do input redirection setup for non-first commands. So if I is greater than 0, in here, we set up standard in redirection from the previous pipe. Here we direct the output of the command into the input of the next command in the pipeline, except for the last command. Then we close all the pipes in the file descriptors, or we close all pipe file descriptors in the child process to clean up. Then we parse the current command segment and prepare argv array. Next, we handle the IO redirections in this function here, next we attempt to execute the command with exec bp. And if it failed, we print this statement for standard error, and we exit. If we fail to fork, we use p-error here. The parent process closes all pipe file descriptors to clean up, and the parent process then waits for all child processes to terminate. Next, I'll go over parse segment, which is a helper function that is called parse segment in process pipeline right here. So what happens in parse segment? So the first thing we do is we create a modifiable copy of the command segment to use for argument parsing. This protects the original command string from being altered. Next, we trim leading white spaces from our segments. Then we Then we loop through characters. We iterate character by character through the command segment, parsing out arguments and handling spaces and quotes. Here we handle quotes, and we toggle the in quotes flag when encountering a double quote. This flag prevents spaces within quotes from being treated as argument separators. Quotes are removed from the argument by shifting subsequent characters left. Then with the argument separation, I'm going to go over parse segment now. So the first thing we do is we make a copy of the segment for stir talk, or for stir token. And next we create these modifiable copies of the command segment to use for argument parsing. Then we trim the leading spaces. And next we loop through the characters. This iterates character by character through the command segment, parsing out arguments and handling spaces and quotes. And if we detect argument boundaries by spaces outside of quotes, it terminates the current argument with a null character, allocates memory for it with stir dupe, and adds it to the argv array. We make sure to capture the last argument. After the loop, we check if there's a trailing argument not followed by a space. It trims trailing spaces and adds the argument to the argv array. And then we go on to the array null termination and cleanup. There, this marks the end of the arguments array with a null pointer. So to get started here, you can see that this code exists in the starting code folder here, tsh, with everything else. And we are going to make clean, make, and start running our tiny shell. The first test we run is just a basic pipeline. We run echo. This is a grep test. There is no output, which is expected. And this test evaluates the shell's basic ability to create a pipeline between two commands. And we're just testing the very first, most basic pipeline to work. Next up, we test multiple pipelines here. And here we get the output that we want. This is an important case to test because you're not only going to see one pipeline, you might see many. The next one we did is a pipeline handling output redirection. So here we have some output redirection where we are outputting it to some file. And so now after running, we now have the output.txt, and this is what was expected. The next test we ran was testing a pipeline with an empty command. We made sure that it would handle this in a way that was not horrible. It doesn't fail. It just handles it gracefully. Ba-boom. It's an important test to make sure that it handles errors and empty commands. The next command we run is with line counting. This also works, so we get another output file called count.txt that also did not exist before. We open it, and we get 2, which is our expected outcome from executing this command here. This is designed to verify the shell's handling of complex pipelines involving text processing works with redirection. And yeah, those are the 5 tests that we ran.